Hello class, this is Mrs. McClellan and we're starting off the year with a unit on astronomy, but we're actually going to spend a few days in the lab activity talking about density first. So you might be asking yourself, well, why are we starting with density? We learned that in middle school. So I want you to just take a minute and think to yourself, well, what does density have to do with earth science? I'm literally going to pause for a moment and let you think about that. Come up with an answer. Maybe weather came to mind when you thought about it. As we talked about, we're not really learning about weather this year, but weather is a really important topic in earth science, and how clouds form and how air movements and air masses move have a lot to do with weather. You might have thought of planets. You know, there's planets that have a higher density than Earth does, and there are planets that have a lower density than Earth. And you might wonder, well, why do different planets have different densities? What gives them their density? And is there any pattern to the densities of planets in our solar system? That's something to think about. Is it random, or is there a reason why they have the densities they do? And maybe you know something about the layers of the Earth, thinking back to sixth grade Earth science, and you know that there's sort of a denser core in the middle and lighter layers on top, and maybe that's coming to mind for you. And all these answers would be correct. So in fact, density is a physical property of matter that affects a lot of the topics in earth science. So that's why before we even get into astronomy and get into the meat of our content, I want to just spend a week really getting our first lab activity done and making sure everybody can calculate density and has the lab skills necessary and a good foundation to move forward. So as we've mentioned before, and you learned this in middle school, density, as you know, is the degree of compactness of a substance. In other words, it's how much stuff is in a given space, to give it a less scientific term, right? So you know that if you had a cube of styrofoam and a cube of lead the same size, obviously the lead is denser. There's literally more molecules packed into that space. So that's part of what density is. And then of course we have the formula density equals mass over volume, which you've learned before. And our typical units for mass are grams given in G, or and for volume could be either cubic centimeters or milliliters. And typically we use milliliters for liquid and cubic centimeters for solid, but it actually really doesn't matter, and you can use them interchangeably. Water has a density of 1. It's 1 gram per cubic centimeter. It's very convenient. That's how the metric system was sort of designed. It was designed around water. So it's an everyday substance, and that's the one density you should have memorized because it's so easy. So just remember, water is 1. And you might also know that when things are heated, they tend to expand, right? Gases and liquids will expand when they're heated. So if you have a certain amount of mass, but the volume is increasing, what's going to happen to the density? Right, it's going to decrease, right? So when something's heated up, you have the same mass, but in a larger volume, the molecules are moving faster, and so it's becoming less dense. And if it's less dense than the other fluids in the area, it will rise. So this can lead to something called a convection current, as colder, denser fluid sinks to the bottom to replace it, and the warmer fluid rises to the top. And this can cause sort of a cyclical pattern similar to what you see in like a lava lamp. We see convection currents in the atmosphere as warm air rises and cooler air falls to replace it. You can't have an absence of something or it creates a vacuum, so colder air will move in to take its place. We also see this happening in the mantle and the earth, the convection currents, where warm magma from the core rises to the surface and cooler material from the surface is slowly sinking to replace it. So here's a simple image of, a Bunsen burner and a beaker of water, and the red arrows represent rising hot water moving to the top of the beaker, and cooler water on the edges away from the flame is coming down to replace that hot water. And that creates a convection current, and you see this on a stove if you boil water. If you were to add pepper flakes or something where you could actually see the water moving, you would see this sort of cycle of rising and falling in the water happening. This happens on the surface of the earth, right? So the sun passes through the air as solar energy, and when it hits the surface of the earth, it turns into conductive energy and warms the earth, and that warms the air that's sitting on top of the earth. That warm air will rise. As the warm air rises, if there's moisture in the air, as it gets higher away from the earth, it cools, and that moisture can condense into water droplets. And that's part of the explanation for how clouds form. We see these sort of convection currents in our planet. So if you look at the equator, right, the equator is where the sun is hitting most directly at almost a 90-degree angle, well, certain times of the year. So you have the strongest energy from the sun hitting right at the equator, so you have the hottest air there. So that warm air is rising from the equator, and if you trace the red arrows, it's rising and moving either north or south away from the equator, and around 30 degrees north or 30 degrees south, it then sinks as it cools, and the cooler air is replacing that warmer air at the equator and making kind of a cycle in the atmosphere. So you have air at the surface coming south from 30 degrees north towards the equator, and air from 30 degrees south moving north towards the equator, and these create winds. So we have these trade winds, and the reason why they're kind of curved and they're not moving in a straight angle to the equator is because the earth is spinning, so it creates an effect that bends the wind. And there's other convection currents that create the westerlies you see between 30 and 50 degrees. Here's another visual of it that's just maybe more simple. These convection currents between 0 and 30 degrees are called Hadley cells, and they're the strongest ones. So the trade winds are really strong, and sailors knew about these and used them for the triangle trade you might have heard about in social studies class, right? They would use these to get across oceans. Convection in the earth, maybe you've heard of this in plate tectonics in 6th grade, but there's a lot of evidence that the mantle is moving. The plates which the continents are part of and this ocean floor make up are sitting on top of a partially melted layer called the mantle, and the plates are solid and stiff on top, and they're moving because of this heat can cause an upwelling, such as we see in the middle of the ocean, which causes a crack in the seafloor, and actually new rock is being made there, like volcanic eruptions and activities happening in the bottom of the seafloor. And it moves sideways away from the upwelling, pushing the plates with it, and then it cools and sinks further away and moves back towards the core where it gets heated again. So we think of less dense things rising, but we can also think of denser things sinking, right? So if you have a mixture or a suspension, usually the most dense materials will sink to the bottom due to gravity. A little physics recap if you're a physics person, force is mass times acceleration. So in this case, the force of gravity is due to the mass of the substance times the acceleration due to gravity. Well, the mass, if there's more mass per volume, gravity is always the same, but if there's more mass per volume, the force due to gravity will be stronger, right? So in this diagram, the force due to gravity pulling the honey is stronger than that of the syrup or the soap or the water, etc. We see a similar pattern in the Earth's layers. We have, scientists have been able to create sort of an X-ray view of the Earth due to seismic waves. Those are earthquake waves. We can tell the density of the Earth, and we'll learn about that more when we get to earthquakes. But for now, let's just leave it the fact that we do know the density going down into the earth, and based on our inferences and our measurements and calculations, we have a really dense core in the center of the earth, and it gets sort of progressively less dense towards the top, and there's distinct layers with distinct densities. And the least dense is the lithosphere at the top of the earth, where you have the crust. So it's kind of interesting, and we can make predictions about what those layers might be made of based on their depth and their density. So even though we've never drilled to the center of the earth, we have some understanding that there's something really dense, probably a metal. They think it's iron and nickel, based on evidence we found from meteorites that have fallen to the earth. So that's pretty cool. We can tell a lot about what's inside our planet just based on knowing its density. And we see this in other planets as well. We've been able to make some rough calculations about what could be inside other planets. And we know this because we can calculate the mass of a planet based on its gravitational effect on other planets and objects near it. And then from knowing the gravity, we can calculate the mass. But then we can get samples of it and say, well, hey, like for example, we know what the moon is made of because we've been there, or we know what Mars is made of because we've sent rovers there and taken samples, and we know it has a sort of rock silicate surface, but it can't be the same density all throughout, because otherwise it wouldn't explain the mass we're detecting based on gravity. So there must be something denser in the core of all these planets, and even though we don't know it for a fact, because we haven't maybe landed an object or drilled into it, we're pretty certain that all these planets have a core similar to Earth. So that makes you think, all right, well, if Earth has a more solid core, how did it get that way? How could something sink if a lot of the material on the Earth is solid? Well, there has to be an explanation, right? One thought is maybe it wasn't all solid. Maybe at one point in Earth's history, things were hotter and more liquid, right? And so if you had a very early Earth that was extremely hot, and so hot that metals were melted and rocks were melted, then the more dense materials like iron and nickel could sink to the center of the Earth and consolidate there. And the lighter materials that have like silicate rocks are made of silicon and oxygen, which are lighter atoms, they would kind of float to the top. So it's weird to think of something like quartz and granite floating, but in a way those materials are lighter, right? And so the surface of the Earth is kind of floating on top of these more denser inner layers. And the only way things could have become layered is if everything was kind of hot and liquidy at one point and could sink to the middle, right? Because of course if you took some iron or nickel now and dropped it on the surface of the Earth, it's not going to sink to the middle. So there must have been a time when things were hotter and moving around and more liquidy. So our first lab we're going to start is on calculating the density of a mineral. Now I know you know how to calculate the density of an object using water displacement. So truth be told, the purpose of the lab isn't really to calculate the density of a mineral. The purpose of the lab is to review some lab skills and to really think critically about some concepts such as percent error, treatments versus trials, how do you know if your data is sort of statistically significant. We're going to learn how to plot and graph the data using Google Sheets, and we're going to find linear regression curves. So there's a lot more going on than just finding density of a rock, because I know you know how to do that. So I want you to come into this lab and realizing that this is not just supposed to be an easy repeat of a middle school experiment, but we're going to do some high-level kind of critical thinking and mathematical analyses with your data. And the analysis is where we're really going to be pushing the sort of honors 10th grade level material.